Okay, so I realized that the counting is actually a hard topic, okay, and it could be much more difficult. Hopefully, you find these to be relatively easy and they correspond to these questions. So if repetition is allowed and if you can specify the order, that belongs to the first class of problems. This is not permutations. It is using the multiplication principle. Okay, so all you have to do is to do 31. And for the second, you can also choose any of the 31 flavors. And for the third, you can also choose any of the 31. So think of 3 boxes to be filled, each with any of the 31 flavors available at the store. Okay, so this is 31 to the cube or to the third power, that's 29,791. So if you have 29,791 people going to the store, possibly every one of them can come up with a different triple count under these conditions. Okay. Now the second one, you can repeat, you cannot repeat. So no repetitions allowed, but the order matters, right? So this is a what? This fits the category permutations. You are looking for how many permutations are there if you had to choose 3 out of 31. And the answer, remember you have 3 boxes to fill, 31. And once you choose the 1 for the first one, then you only have 30 to choose from for the second flavor. And that will leave you with 29 choices for the third. If you multiply these numbers, you get 26,970, slightly fewer than when the repetition was allowed. Okay, the third one, the most complicated one, is when the order does not matter, cannot specify the order, and you have to pick with no repetition. So this is the hard one, right? Again, you choose, this is a combinations problem. Okay, let's try to figure this out. If the order were important and repetition was not allowed, okay, this is the number, 26,900, close to 27,000. That's the number of permutations, okay? But in this case, remember vanilla, chocolate, strawberry would be considered the same as chocolate, strawberry, vanilla. And a few other cases, right? So if you pick 3 choices like chocolate, vanilla, and strawberry, there are 6 different ways of saying that in different ways, right? So you have to divide this number of permutations by 3 times 2 times 1, that's 6, because there are 6 different ways to write the same combination, I mean, the same combination but different permutations. So then you divide this number by 6, and that's how you can get the answer to this. This is much, much less or fewer than the other 2 answers. That's 4,495 different ways. Okay, and that's because the order doesn't matter. And you are, again, counting each combination with 6 different permutations, and that's why this number is drastically less. Okay, so hopefully you've gotten these answers. You get to do a lot more problems. Some of them are complicated in your homework, but those are important as you prepare for the test that covers this section. Okay, so the second part, last part, is a little shorter, is the idea of expected value. This is the average value gain or loss of playing a game, right? When prizes and probabilities are given. So, and again, I can theoretically present this, but I'm not going to do that. The theoretical aspect or the approach to this problem can be pretty difficult and could be quite messy, right? So I will teach you this, again, in the context of, let's say you play a whole bunch of games. How many of those games are you going to win and lose? And how much money would you gain and lose, and so on. Okay, so here's the first example. Let's say you roll a die, okay, a simple die, and a standard fair die, and you win $6 if the outcome is a 1, but you lose $2 otherwise. Okay, now $6, that's a good winning, but you don't win that many times. In fact, you win only 1 out of 6 times, right? Because getting a 1 has a probability of 1 out of 6. You lose 5 out of 6 times, and each time you lose $2. So the question is, here's the question. If you play this hundreds and hundreds and millions of billions and billions of times, theoretically, then how much do you expect to win each time you play this game? Okay, that's the question, not like how much are you going to win the first time, because you don't know. But if you play this hundreds of times, there's a thing called the law of averages or law of large numbers. And that's going to tell you that your winning percentage is going to approach the theoretical approach. In this case, it's 1/6, and you will lose 5 out of 6 times on the average, right? So here's the way to think about this. Let's play this 600 times. Now, the reason I choose 600 is because you know that 1/6 is the probability of winning, right? Winning, you win 1/6 of the games. And how much is that? That's 100 games. Okay. So 100 times you win, and you lose 5 out of 6 times. And that's 500 games. So if you play 600 times, does it make sense that you win 100 times and you lose 500 times, right? If it's 6,000 times, then you win 1,000 times and lose 5,000. And each time you win, you get $6. Okay, so after 600 times, after playing this game 600 times, you expect to win $600. This is called your net, or no, this is called your winnings, right? And how much do you lose? Each time you lose $2. Put -2. Okay, and so that's -$1,000. Let me not have this thing in here. Okay, so after 600 games, you will have gained $600, but you would have lost $1,000. So the net gain is going to be -400. Make sense? All right, so then you come up and divide this 400 by 600, because that's how many times you played this game. So the average is -0.66. All right, so what does it mean? This is the expected value, right? The expected value is, I don't have a place to put it. All right, so this is, the expected value is the loss of 66 cents per game. Okay, now, you know, you can play 600 times, but the point is, if a casino is operating a game or games, they may have 5 million people, all right? And if each person loses 66 cents each time they play, now we are talking about millions and millions of dollars that people lose at the casino, that converts to millions of dollars gain for the, the casino. So what is the best way to earn money by gambling? To own a casino, because the expected value is always going to be, it's designed to go against you, okay? And in other words, in every one of these gambling situations, the expected value is negative for the player, okay? And so yes, there are some exceptions, but overall, you know, this is how it's designed. Anyway, so the expected value answers the question of how much are you going to win or lose on the average every time you play a particular game. Okay, next one. Oh, by the way, the key way to answer this question is to play a whole bunch of games. And so think of a large number, and so that you can do this kind of argument to come up with an answer. Again, there is a formula which is much more complicated, and it will give you a very messy calculation. And I'm not doing that. This is a much better way to think about this. Number 2. Pay $1 to play a lottery game. Okay, you're going to play, every time you play a lottery game, you pay $1. 1 out of 100 people wins $10. 1 in 1,000 will get $500. Okay, so that's a great thing, huh? Well, how much do you expect to win every time you play this lottery? Think of buying a whole bunch. Okay, so the thing is, if you are trying to apply a formula or something, then you would have to convert this into positive and negative, and then count the expected value and multiply the probability by the winning for that, and so on. You don't have to worry about that. Think of playing this many times. If this lottery is going to print 100,000, tickets. Then think of buying all 100,000 and theoretically see what happens. Okay. Now I think for this one, let's say what you want to do. Maybe 1,000 tickets. Okay. Now you can choose a good large round number. You can do 1,000,000 if you like. 100 maybe too small because you have 1,000, 1 in 1,000 chances. Let's say you buy 1,000 tickets. Okay. Now the cost is, of course, if you buy 1,000, every time you buy a ticket, you lose $1. That's how much it costs. So you lose $1,000 just by playing 1,000, by buying 1,000 tickets. So $1,000 is your loss. But 1 out of every 100 people wins $10, right? Now, how many people win? So 1 out of 100, okay, this turns out to be, this is part of your winnings. 10 people, or 10 of those tickets. See, you buy 1,000 tickets. So theoretically, 1 out of 100 will win $10. So 10 of these tickets will win $10, right? And so that's $100 you win because 1 out of every 100 tickets will win $10. And then 1 out of 1,000. Okay, now you bought 1,000 tickets. So one ticket, one of those 1,000 tickets you buy is going to win $500. Cool, okay? So one of those tickets is worth $500. 10 of those tickets is worth $10. But in buying 1,000 tickets, you just lost $1,000, right? So what's the net value here? Plus 100, plus 500, minus 1,000. That's $600 gain. And then you have $1,000 loss. So the net loss for you is basically $400. Okay, so you basically lost $400, but 400 divided by the number of tickets you bought, that's $1,000. That's 40 cents. Okay, so you can say the expected value for this kind of lottery is minus 40 cents. Okay, and in everyday language, what this is saying is that every ticket you purchase, you expect to lose 40 cents. Yeah, exactly. And a real lottery game is a lot more complicated, but truly the expected value for the lottery player is always going to be negative. Okay, and you can comfort yourself saying, yes, but I am contributing to the education system or something. Sure, that's great. Okay, after a touchdown in football, okay, you see touchdown, almost always touchdown is followed by that extra point, the field goal attempt, right? But there's another way to get 2 extra points, and that is if you try to pass and or run, and if your ball crosses the goal line and not with the field goal attempt, then you get 2 extra points. Now, you don't see this very often because this is much harder, right? But what is the expected value difference? After a touchdown in football, suppose there's a 94% success rate for a 1 extra point, by kick, and a 37% success rate for a 2 extra point play. What is the expected value of each, right? So that's easy, and I think that's an easy one to do. For the 1 point attempt, you have a 1 point with a 95. Okay, let's say you try 100 times. Maybe remember, this is a good way to study these things, just by starting with a large number, nice number. If you attempt a 1 point, 1 extra point, basically field goal attempt for that 1 extra point, 94 times out of 100, you get 1 point. Okay. Now 6 times you fail, and you get 0 point. Right? So that is 94 extra points if you do this 100 times. Now, if you try to go for 2 points, okay, and some people do, sometimes it's important if you want to win by that 1 extra point or whatever, as opposed to tying the game. So then you get 2 points, but this only happens 37 times out of 100, okay? And the other, that's 37, And then the other is 63 times, you fail and get no points. So this will be 74. And so the probability or the expected value is 74 out of 100 attempts. And while if you try for 1 point, that's almost a certain way to get 1 extra point, you get 94 points after 100 times, right? And so that's why, again, most teams will prefer to go for the 1 extra point as opposed to the 2 extra points, all right? So that's, again, the decision is made based on expected value. And so that certainly makes sense. Other examples of expected value, it basically is dictating everything you do all day long, every day. Right? Should I drive at 80 miles an hour to make it to my math exam? Well, yeah, I mean, if everybody else is doing this, the chances are that it's very unlikely that you get caught and have to pay the fine. So maybe people do that. How about if I have to drive at 90 miles an hour, or 100 miles an hour, or 110 miles an hour? Okay, that's dangerous because the cost, if you get caught, and there's a percentage of chance that you get caught, and then the expected value is quite high that you have to pay the penalty. And that's going to be an expensive thing, right? And so most likely you probably would not be driving at 100 miles an hour. And in fact, you should never do that, right? Should I park illegally? Let's say you find a place to park, but it's designated for the ones with disability plate, and you don't have a disability or disabled license plate. Can I park in that the disabled parking space for 5 minutes if you absolutely have to? Yeah, you may, if you think that, again, the probability of you being caught is very little. But how about an hour? No, you don't want to do that. I mean, those are like what, $500-600 fine, right? So you're always analyzing, mentally calculating the cost and the profit, the gain and the loss, right? And so everything is sort of like a balanced act, and the expected values play a very important role. Government knows that, policymakers know that. That's why they want to have a heavy penalty for something serious, right? Because that would cause the expected value to change. What are the details you need to know this calculation? The penalties, and then the probability of being caught, probability. So these are the things that you need to know in order to do these calculations. But like I said, we calculate risks and we live accordingly. Right? So the idea of expected value is very, very common. And in fact, we implicitly calculate the expected value for pretty much every action we take. All right, so that is how important the idea of expected value is. Okay, so this is it for lesson number 11. Next time we'll start a new chapter on statistics, all right? And that's also related to chances and probability and casinos and places like Vegas. Hopefully, you have learned some important lessons about, chances, probabilities, and expected values, because these things really do affect our lives every single day. All right, so until lesson 12, I hope you have a great week, good day, and I will see you later. Okay, bye.